Welcome ENET 130 at Bellingham Technical College's quarter study or half-quarter study of semiconductors. So for this recorded lecture, we will be taking an abrupt turn from our previous studies of bipolar junction transistors and diving into a completely different type of semiconductor device that also functions as a transistor. And this is known as a field effect transistor. There are two main types of field effect transistors, one known as a junction field effect, which is what we'll address in this lecture, and a similar one with a slightly different gate interface arrangement known as a metal oxide field effect, MOSFET, or otherwise known as insulated gate, for reasons that we'll explain later. So, general idea of a transistor. Like in the case of the BJTs, field effect transistors are going to allow us to use a small signal to control a larger signal. That's the whole idea of transistors in semiconductor or vacuum tube devices. Small signal controls larger signal. But rather than doing it by having a small current control a larger current, or a current control current source, which is what bipolar junction transistors do, a field effect is going to use a small voltage signal to control a much larger current signal. So it's a voltage control current device or current source. Okay, the easiest way to understand how a field effect transistor works is to look at a schematic. So this is a schematic here in Mr. Fiore's figure 10.1 of what's known as an N-channel JFET, or an N-channel junction field effect transistor. Okay, so when we put this device into a circuit, the main current that we're going to try to control would be flowing between source and drain. This would be analogous to our collector emitter current. We're going to control that by putting a voltage signal V signal between the gate and the substrate. So you can think of the gate of a field effect transistor as being like the base of a BJT, and the source and drain as being like the emitter and collector of a BJT. Don't think of that too far in terms of how you would hook the circuit up, though, because the actual biasing and arrangement is totally different because the mechanism of control is very, very different. But in terms of where the little control signal goes and where the larger controlled current flow goes, that's the one-to-one. Source and drain are like emitter and collector, and gate is like the base. Okay, I have highlighted alternating colors in terms of the steps that you go through to understand how these work when we bias them to give ourselves control, along with some tips of important terms and regimes of operation. I'm not going to read through all this, but I'm just noting that this is to help you, these annotated notes when you do your studies. But I'm going to point out some notes over here that I've added in the right-hand margin. Some regimes of operation that are really important. Okay, let's start out where the gate is open. We don't apply any signal. If we just want to flow some current between source and drain, we've just got a big piece of a single monolithic semiconductor material, which is, as long as we get across whatever junction potential at the metallized contacts on the edges, no problem. I can flow current through this. This is going to act like a reasonable conductor with just a little bit of forward voltage. So there's going to be negligible resistance to current flow. As it turns out, it's not going to act exactly like a resistor over all source to drain voltage ranges. We'll get to that a bit later, but generally speaking, it's not like the double junction of a BJT between the emitter and collector, where if we don't apply a current to the base, it's open. The JFET is default open. So if I don't do something with the gate, I can flow current source to drain. Where my control comes in, and we term it throttling, is when we apply a voltage source to the gate. And in that case, we're literally going to pinch off that channel. So we're going to go down to figure 10.2 to give you an idea of the actual mechanism of current control in a JFET. So this is how we get our control in the device. So we're going to reference basically a common. As you can see down here, we're going to put two voltage sources. We're going to have one labeled VGG, which is basically ground or common to gate, and then we're going to have one that is biasing the drain versus a common. So if we think about our bottom wire here, where I'm moving the cursor as being kind of like a ground or zero, the source is effectively a ground, and as we come up through this voltage source, we're actually going to drop. So this is in backwards. So we're going to apply a negative voltage to that p-type semiconducting material at the gate. Important thing to note, and I'm going to circle this because it is so important. Field effect transistors are very current sensitive devices, as all semiconductors are, but these are particularly so. Do not neglect your current limiting resistors, especially at the gate, and this will be even more important with insulated gate, the field effect transistors. We are not going to flow any significant current through that gate. We're going to bias it and create a voltage field, which is going to create a depletion zone down in the channel. So this is very important, our current limiting resistor. Do not forget that. It's a circuit safety design. So our gate has a negative voltage applied to it. Okay. In our p-type material, remember, we have a lot of positive majority charge carriers, a lot of holes. We've doped that p material with that trivalent dopant. We've effectively introduced a lot of positive charge carriers. Well, when we apply a negative up here at the metallized contact, all those charge carriers are going to go stampeding up towards the contact and away from the junction. So we're going to create an effective negative charge in the p material, especially up near the p-n junction, and that's with these negative signs with the circles. Remember, a circle means a charge that is an effective charge because we've withdrawn what would otherwise have been there. So we kind of withdraw our natural p dopant holes from the interface. We create a net negative charge at the interface. Charge balance has to happen, and remember, a p-n junction acts a bit like a capacitor. So the more we withdraw our hole dopants from the interface in the p material, the more the n material in the channel adjacent to it responds and says, wow, there's all this net negative charge. All of the electron majority charge carriers in the n channel are going to go, whoa, I don't want to be near something of a like charge, and they're going to withdraw from the interface, and we're going to end up with a depletion zone. Those majority charge carriers are going to withdraw from the interface, and they're not going to be available. So we end up growing. The more we apply a negative voltage to the gate, the more we grow a big blob of effectively intrinsic semiconductor material out into the n channel. Well, as we all know, without those extrinsic charge carriers, that n-type material can't conduct very well. So what we're doing is effectively growing a big resistive gate, a valve, so to speak, out into that n channel. And so the cross-sectional area, the literal physical cross-sectional area for current flow, shown here with the red dotted arrow, goes down. This is akin to sticking your heel on a garden hose and cutting off the flow by pinching the hose, or an iris gate, or any kind of gate in a pipe, where as we close the gate down or we close the valve down more and more, the flow drops. No matter how much pressure we have, if the valve is shut or partially shut, we limit the flow. That is exactly what this voltage signal gate to source is doing. It's actually gate to ground, but the source is at ground. So as we increase our source to gate negative voltage, we limit literally the cross-sectional area through which we can flow current, and so we limit current flow. There is our mechanism for control. Source to gate voltage controls source to drain current. So there's our voltage controlled current source, and that is the essence of how JFETs work. Generally speaking, there is less difference in source to drain characteristics in the device than necessarily collector to emitter. They are not necessarily interchangeable, so please don't hook them up backwards. They won't work as well. But the big difference is gate to source or gate to drain. Our current is going to flow source to drain. Okay, so let's look at how much current flows under what conditions of source to gate throttling, so to speak. And so to do that, we again construct some characteristic curves. So to get the curves in figure 10.3, we sent someone into the lab, say, and said, okay, put an ohm meter here after your drain current limiting resistor and measure how much current flows for a given source to drain voltage. So this voltage is actually applying our supply for current flowing source to drain, and under different conditions of source to gate throttling. So start with it wide open and then keep applying more and more voltage source to gate and see how much current flows through here as you turn this dial. So here's our plot. So here's our measured quantity, our drain current, and on our x-axis here's our source to drain voltage. So again, this is the same idea we've brought up before, where we're looking at the current voltage characteristics of a device. If I put so much voltage across a device, how much current flows under what other conditions? And in this case, our other conditions is our gate to source applied quote-unquote throttling voltage. Okay, so let's start in a condition where our gate to source is 0. Well, we're gonna leave it wide open. We're not gonna try to pinch down that N channel at all. Okay, in that case we start with no voltage across the source to drain, and so there's no current flowing. Surprise, surprise. But as I start to apply more voltage between the source and the drain, my current coming out of the drain rises almost linearly, like a resistor. It goes up, and because it's linear, like a resistor, it's called, not surprisingly, the ohmic region. So for small applied drain source voltages, a JFET is going to behave a bit like a resistor. Then it's going to hit a point, now here's where it stops behaving like a resistor. It's going to hit a point, now remember, this is independent of the gate throttling. This is just the source drain characteristic on its own. So it's going to behave like a resistor up to a voltage V sub P, V peak. And this is something to look for in your spec sheet. That'll be listed, that's a device characteristic. At that point, the curve heals over and becomes almost constant. Its slope is only due to whatever ohmic losses there are source to drain, which are not much. And so we get this almost constant current plateau. So you've wondered about what type of devices actually can produce a current source, an ideal current source. And boy, this is looking pretty much like it. So for a given range of applied voltages, I get a very consistent current. So this is a nice current source device. But of course, there are limits to all things, and if we apply too much voltage between the drain and the source, the device will break down and will conduct a lot of current and probably melt the device. So this is known as breakdown voltage, drain to source, and that represents the upper end of our operating regime, drain to source. So don't go above this in your circuit, and that's another maximum to look for in your spec sheet. Okay, so this plateau, that we've now defined under conditions of no gate throttling defines another spec characteristic, and that's I drain to source steady state or saturated. That's the most current you're going to want to ask that device to give you on a steady basis. So that's another kind of operating limit of the device. Okay. Now, what happens if we apply some gate to source voltage? And of course, in the negative direction, so we're now pinching down that channel. Well, if we do that, we just end up following one of these other curves. So the first thing we'll notice is in our ohmic region, the slope is a little less. So we get a little less current for a given drain to source voltage. And most importantly, our plateau is lower. So, and the breakdown voltage is unchanged, so still don't want to go above that. That's big no. So we can pick our plateau, whatever constant current we want, by understanding this relationship, knowing what these curves are and maybe some function that relates them, and how much gate to source voltage. So if I want the full saturation current in this constant current regime, I don't apply any gate to source voltage. If I want, say, maybe half of it, in this case I apply -1 volt gate to source. So I can tune the nice steady constant current that I can have flow between the drain and the source independent of drain to source voltage. So a constant current source basically by the gate. So here's where our gate signal controls the level of this plateau, and to a lesser extent it also controls the slope in this region, but this is the real effect. So we pick our steady constant current with our gate to source voltage. So it's nice having all these curves, and I could draw some graphs and extrapolate. It would be even handier if I had a little mathematical function where maybe if I knew some of these spec parameters, maybe if I knew my max current steady state, and I knew maybe the gate to source current that completely pinched off flow. Here's another important one. It defines this kind of almost zero curve. This is the gate to source voltage necessary to completely shut off the drain current, and that's another spec parameter right there. So say I knew this and I knew this, it would be nice if I had a function that I could say, okay, I want so much drain current, how much gate to source voltage do I need to apply to get that in that constant regime? And lucky for us, it's a parabolic relationship. So the laws of physics have been our friend. So this is the relationship between any gate to source applied voltage, that's our signal, remember, the gate to source voltage necessary to completely cut off drain current, basically shut the device down, the complete pinch off of current, and the max current that I can get if I have no gate to source, if I'm not throttling at all. And look, it's just a squared relationship of this term. So drain current is equal to max drain current with no throttling times this whole term, which is 1 minus the ratio of whatever gate to source voltage I apply and the gate to source voltage necessary to completely shut the drain current off, all squared. So I get this term from my spec sheet, I get that term from my spec sheet, I decide what I want here, and I can solve for this term and say, here's how much gate to source voltage I need to apply to get that much current that I might want, and vice versa. Okay. And we can normalize that parabola to an expression for any gate to source voltage. Normalized curves are things that you'll frequently see on spec sheet, and in this case this ratio was just normalized to 1 to make it easier to graph. So you may see these normalized curves on some spec sheets. We saw that with our beta for bipolar junction transistors as a function of collector current. So it's just an easy way of reporting things. And you can work through an example to pick your drain current. Okay, last but not least is a final spec term. It's a bit of a vocabulary term, but it's just another handy way of using that drain to source voltage versus gate to source voltage, control voltage versus our current. It's a term called transconductance, and the symbol is a little g sub m or little g sub fs. So you'll see these on spec sheets. So what is transconductance? Sounds like a big term, but it's really simple, and it's just a handier way of telling us what's going on in our nice parabolic equation. So it turns out it's the slope of this parabola at any given gate source applied voltage. Okay, so unfortunately, for those of you who are algebra students, you have to use a little calculus to get the slope, but that's okay. Mr. Fiore has already done the calculus for you. He's just showing you how you get it. The slope of this curve, let's see, how would that be important to us? Okay, we're going to use this normalized plot. And we'll just look at the y-axis as just drain current. So I'm looking at, okay, I'm going to apply some gate to source voltage, and I'm going to get a drain current. So maybe I'm operating over here. I'm going to apply very little gate to source voltage. Maybe I'm concerned, maybe I can't control that voltage perfectly. So I want to know if I move off of my control point, maybe I can't get quite negative 0.8 there, or whatever I'm trying to apply. Maybe I've got a kind of a sloppy DC power supply. I want to know how different my range of Y values is here for any given change in X. If I move to maybe 0.82 or 0.84, am I going to get a huge change in drain current? Because that could be really bad if that's what I'm trying to control, or is it only going to change a little? So that's basically a sensitivity factor. Well, the slope at this point tells me how much my Y value is going to change for any little wiggle in X. My nominal point is the point on the curve, but the change is dictated by the slope. So if that slope is small, that means I can change the gate to source voltage a little bit, no problem, and I'm not going to get a massive change in drain current. But if I'm operating up here, the slope's a lot steeper now. So if I wiggle between this point and this point, say, I get a pretty respectable change in drain current. And if I need to keep that drain current rock steady, which is probably why I'm using a JFET to begin with, I might not want a really steep slope. Or maybe I do, because maybe I'm trying to control. Regardless, maybe I want to know what it is. That's why the transconductance term is defined and quantified for us, because it's important to know that slope. There's our practical application for transconductance, or the slope of the drain current versus gate source voltage function. So here's how you get it, and you do have to define it in terms of a slope at a 0 point. So we get one more term, vocabulary term, and that's the transconductance sub-zero. So that's the slope of our parabola when the gate to source voltage is 0, so no throttling. So we have to define that, and then our slope is defined by this function. So here's the drain current for any gate to source applied voltage in terms of max drain current, and gate to source voltage to totally cut off the drain current. And here's the slope of this drain current to gate source voltage function in terms of all the same stuff, but instead of max current we've got that slope when we have under those same conditions. So this the slope under the same conditions that apply the maximum. So you use this function if you want to pick a drain current for a known gate source, or pick a gate source for the drain current you want, and you use this if you want to see that sensitivity slope. How steep is the slope of that curve, and how much change am I going to get in drain for any little wiggle in gate source. Okay, and we can do all kinds of math with that and relate them. So I will refer you to Mr. Fiore's the rest of his section if you just want to know mathematical relationships between different terms, if maybe you only have one listed on a spec sheet, or if you need to know a relationship. These two equations, 10.4 and 10.5, if you'd like some math, you can derive them from these others. But it's more important for us just to know what they mean. Slopes versus drain currents in terms of what function of gate source. Okay. Last but not least, figure 10.6. What if we want to pick these nifty devices off of a schematic? And this is how we denote them. Symbol is very different from a BJT. Mainly we have kind of perpendicular little lines. So we've got kind of a long bar that represents the gate, and then the arrow pointing from the gate into the device versus out of the device tells us whether or not we have an N channel or a P channel. So an N channel is denoted here on the left, N channel, and this is P channel. And of course the main difference is the polarity that we apply between the gate and the source to create the depletion zone is dependent on whether we've got a P channel or an N channel, and basically the polarity of the interface. So we still have one monolithic material that we're going to flow current through, but N channel and P channel really has, even though it's a difference in channel material, what it really means to us when we use a circuit is what polarity of biasing do we need to pinch down that channel to grow that depletion zone. So arrow direction is super important, and then knowing effectively what lead to what. So main controlled current is going to flow this way, and voltage signal between gate and source. And that is it for junction field effect transistors, as well as general theory of field effect transistors generally. Next lecture we'll go into a variant on this, insulated gate, very similar with a few little exceptions and a little bit additional functionality, and that will conclude our study of field effect transistors. We will not be applying them in circuits the way we have BJTs, but know that basically the same kind of amount of circuit control can come from them. But basically we're going to use, anytime you have a field effect, you will use a voltage signal to control current rather than a current signal to control current as in a BJT.